We did some good science by looking at the individual gas laws, Boyle's law, Charles' law, Gay-Lussac's law. But what we want to do now is try to organize those things and put them into something that's a little more workable and less cumbersome to deal with. So just a reminder, we have Boyle's law, which relates pressure and volume, and we found out that volume was proportional to 1 over the pressure, or they're inversely proportional. We have Charles' law, which told us that volume was directly proportional to temperature. Then we have Avogadro's law, which told us that the volume was directly proportional to the number of molecules. So if we put all these things together, we get that the volume is proportional to the number of moles and the temperature, and inversely proportional to the pressure. Of course, like we did with the individual gas laws, we can take that relationship there and turn it into a mathematical equation by saying that volume is equal to a constant, and we're going to give that constant the value R times NT over P. This then is our ideal gas law equation. Now it's much more familiar in another form. PV equals nRT. It tends to roll off the thumb a little bit better, or off the tongue a little better. PV equals nRT. So we tend to see it in this form. If we, let's go on to the next one. So there's our PV equals nRT. If we rearrange this and solve for the R, so R equals PV over NT. Depending on the values that we put in for pressure, volume, number, and temperature, we get different values for R. Now we will, by and large, use the one where we use liters, atmospheres, moles, and degrees Kelvin. So it's a 0.08206 value. We will use this one, and we probably have already when we talk in terms of energy units. So that's the one that has the joules per kmol. The one below it is calories per kmol, and then there are the ones where we use, we have meters cubed for the volume, pascals. So that's more of our physics-derived units, and you can see that actually corresponds to the derived units of the energy up there, and then liters torr per kmol if we're using those units. Now, if we rearrange that equation for volume, we get volume equals nRT over P. And if we put in 1.0 moles for our number of moles, R 0.08206 liter atmospheres over kmol. T, we're going to use standard temperature, 273 Kelvin, and standard pressure, 1.0 atmospheres. Okay. So if we use all those values there, we get a volume of 22.40 liters. Right. So this is the volume of an ideal gas at STP, standard temperature and pressure. All right, now, just to kind of give a little foreshadowing down the road, all right, here we have, significant figures, this would be 22.41 liters. Okay. if we look at the list of gases that are provided here, we see that not all of them, actually, very few of them are actually right at 22.4 liters at STP. Chlorine is quite a bit below that, 22.06 liters. Carbon dioxide a little bit below that, and then we've got ammonia and nitrogen, helium, and hydrogen, which tend to be pretty close to that. But this just gives you an idea that this equation works for what we refer to as ideal gases, not necessarily real gases that we actually work with. So we'll take a look more at that toward the end of the chapter. For right now, what we want to do is focus in on how do we solve problems using PV equals nRT. So there's two advantages to using PV equals nRT. The first one will get demonstrated in part A of this question, the second one in part B. So first we have many gases are shipped in high pressure containers. Consider a steel tank whose volume is 65.0 liters, which contains hydrogen or oxygen gas at a pressure of 16,500 kilopascals at 23 degrees Celsius. So what mass of O2 does the tank contain? So let's focus in on just that first part. What mass of O2 does the tank contain? Well, obviously, from the PV equals nRT, we're going to need to solve for moles. And then once we get moles, we can convert to grams. So if I rearrange my equation, I get N equals PV over RT. Now, unfortunately, our values aren't quite in the units that we would want, so we're going to need to do some conversions here. So my pressure is in kilopascals, so I'm going to do 16,500 kilopascals, and my conversion is 101.3 kilopascals to 1 atmosphere, which gives me a pressure equivalent of 162 atmospheres. I go to plug that in, so we have 162 atmospheres. Volume is given to us in liters, so it's 65.0 liters. R, 0.08206 liter atmospheres per K mole. And our temperature currently is in Celsius, so all we need to do is add 273 to get to Kelvin. So it would be 296 Kelvin. Again, that's 23 degrees Celsius plus 273 to give us the 296 degrees Kelvin. This will then give us the number of moles of oxygen. And that works out to 436 moles of O2. Use our stoichiometry, 436 moles of O2, and 1 mole of O2 is 32 grams of O2. Moles cancels out. And we get 15,300 grams of O2, or 15.3 kilograms of O2. So that would be the mass of the O2 that would be found in this cylinder. Now let's take a look at part B of this and see how we can use the combined gas law to, the ideal gas law to help us organize this problem. So part B says, at what temperature would the pressure in the tank equal 1,500 atmospheres? So here we're looking at the relationship between temperature and pressure. So what I'm going to do is I'm going to take my equation and rearrange it to put temperature and pressure on the same side. So if I do that, I have temperature over pressure is equal to, and it doesn't matter which one I put on top or the bottom, is going to be equal to V over NR. Okay. So the V over NR, so the volume is going to stay constant, N is going to stay constant, R is going to stay constant. So the whole right side of this equation is our constant, which means that T1 over P1 will equal T2 over P2. So we're trying to solve for the temperature in the tank at a second pressure. So in this case, we're solving for T2. So I could put down T2 would be equal to T1 times P2 divided by P1. Then just be a matter of filling in our values here. So our initial temperature is the 296 K. Our final pressure is going to be 150 atmospheres. Our initial pressure, go back to the other problem, our initial pressure was the 162 atmospheres. And so if we do the calculation, gives us 274 degrees Kelvin for the temperature, which if we subtract the 273, we would get 1 degree Celsius. So this demonstrates how we can look at an individual one of the gas laws from the standpoint of the combined gas law equation. So that's the only thing we would have to remember there. And one more. So if we look at the letter D here, and we're trying to figure out the pressure of the gas if it were transferred to a container at a different temperature and a different volume. So we're changing pressure, temperature, and volume. So if we put all of these over onto one side of the equation, and let's see, the pressure of the gas. I'm going to put the pressure on the top this time. So we'll put pressure and volume on the top and temperature on the bottom. So I'm just rearranging PV equals nRT. And so we end up with N and R as the values on the right. And again, for this situation, the number of moles in R are going to be constant. So what this gives us then is P1 V1 over T1 equals P2 V2 over T2. In this particular problem, then, we're trying to figure out the new pressure. So we're trying to figure out P2. So pressure 2 would be equal to pressure 1, volume 1, temperature 2, divided by temperature 1 and volume 2. So it just becomes a matter of plugging in our values. Pressure 1, and in this case, since we aren't, you notice that R doesn't appear in here anywhere, that we can go ahead and use other pressure units here. So we want to end up with a pressure in kilopascals, so I might as well use my initial pressure in kilopascals. So that was that 16,500. So 16,500 kilopascals. So that way my unit that'll be left here will be kilopascals. My initial volume was 65.0 liters. And my initial temperature was the 296 Kelvin. divided by my new temperature. So I'm going to 24 degrees Celsius. So I believe that is just 1 degree up. Yeah, so it's 1 degree up in temperature. So it would be 297 Kelvin. And my new volume is 55.0 liters. Okay. And I should have done this in the last one, but just to confirm, kelvins cancel out top and bottom, volumes cancel out top and bottom. And if we do the math on this one then, which gives us a pressure of 19,400 kilopascals. Okay, so you can see the versatility of the combined gas, or the ideal gas law equation. And so we'll do a few problems like these in class to get us, comfortable with it.